Assalamualaikum and good day everyone. Today we will learn about the series and parallel capacitors. So what are you going to learn in this subtopic of series and parallel capacitors? For the parallel capacitors, it actually for you to understand in a simple way, it is like you are calculating the capacitor, the resistor in series. Alright, let's go to the details. If you're given a circle like this, parallel capacitors, we can see that these are the capacitors in parallel. So the equation that we can get over here is the current in parallel capacitor should be different, but we know that parallel components, the voltage should be similar. It should be the same. So in order to get this one, if we consider this as the node, okay, node equation, we will consider this as a node equation because in parallel circuit, the current should be different, but you have the same voltage drop across that components. So applying KCL, we will get this equation I equals to I total equals to I1 plus I2 plus I3 plus dot dot dot. So this is the basic equation that we learned last week, where you have I equals to C dV dt. So if you put in the individual current equation, so let's say your current I1 is actually C dV dt, and this is the C1, the capacitor 1. And then if you have the I2, which related to the capacitor 2 times the dV dt, remember that the dV dt over here, for all of these capacitors, the dV dt, it doesn't have V1, dV1 dt or dV2 dt, because we know that the same voltage drop, you will have the same voltage drop across parallel components. So the dV dt should be the same for each of the capacitance. So from here, we can actually simplify the capacitors into C equivalent, which is equals to C1 plus C2 plus C3 plus blah 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 up to Cn. So if you look into this equation, this is similar to the resistor in series. Okay, we just add up all the capacitance value. If you look at the at this slide, so the equivalent capacitance of n parallel connected capacitance is the sum of the individual capacitance. Okay, so in short, the capacitors in parallel combination, you can calculate the capacitance value in the same manner as the resistors in series. Next, we will look into the series capacitors. So if you connect numbers of capacitors in series, okay, this is in series where you will have the same current. Okay, a series circuit will have the same current across all the components, while you have a different voltage drop across each capacitor. So for the series capacitor circuit, we will apply the KVL. So the KVL said that the total voltage drop should be equals to the combination of individual voltage drop. So V1 plus V2 plus V3 and so on. And you should remember that Vk, or the number, which number of the capacitor, V equals to 1 over C with the integration of It plus Vt naught. Okay, this is the initial value of your voltage in the capacitor. So since we have the same current, okay, we have same current for each of the capacitance, but you will have different voltage equation. Therefore, your current, the voltage, the total number of voltage can be equate to this equation, 1 over C1 with the integration of It plus the 1 over C2 and so on. Okay, therefore when you rewrite this combination, you should rewrite the capacitance as this equation. Okay, 1 over C equivalent equals to the 1 over C1 plus 1 over C2 plus 1 over C3 and so on. Okay, and so we can rewrite this into this kind of equation. Okay, T naught T, and you will have the same current across the components. Okay, so this is your and this one is very slow, VT T naught. If you have V2, then you will add up over here. So the point that we want to take is the total capacitors for series circuit. Okay, for the capacitors in series should be equals to 1 over C equivalent equals to 1 over C1 plus 1 over C2 and so on. Okay, let's go into the example 1.5. Okay, so the question is, what is the total capacitance of 4 times 30 millifarad capacitors where it is connected in parallel, and question B is for capacitors in series. So let's solve this one. You have 4 30 millifarad capacitors in parallel. So remember, in parallel your C equivalent should be just the combination. Okay, you just add up all the individual capacitance value, right, plus C4. So that will be like 4 times your 30 millifarad. Therefore, it should gives you 120 millifarad. Okay, whereas for the capacitor in series, you should take this equation as 1 over C equivalent. Okay, so this like you have 1 over 30 millifarad plus 1 over 30 millifarad and so on up to 4. Okay, so from here, if you simplify this, you will get the C equivalent equals to 7.5 millifarad. Okay, this is quite straightforward actually question. Next, in example 1.6, let's determine the equivalent capacitance for the following circuit. So remember, if you are trying to find out the C equivalent from this side, you need to do the circuit reduction. Okay, that's the best way to determine the equivalent capacitance for circuit if you're given the circuit itself. Alright, so in order to do the circuit reduction technique, so we work from right to the left. Okay, the reduction should take from this part, or you can always apply this first. Okay, since this is in series, so remember, capacitor in series, you will do the C over here is 1 over 3 plus 1 over 6. Okay, this is maybe over here you can name it as C1, right? 1 over C1 equals to this, so your C1 equals to 1. Okay, and then from here we can always simplify the equation or the circuit into this one. Okay, this is 2 farad, and then you have your C1 over here, and your C1 is actually parallel to the one with 4 farad. Okay, over here you will have 3 farad. Okay, so now you try to solve this part first. Okay, so from here your C1 is actually 2 farad. Alright, so this is 2 farad, the other one is 4 farad, so this is in total gives you 6 farad over here. Okay, now everything is in series. So in series, you will have this kind of solution. Okay, so the simplified circuit just now is something like this. Okay, over here you have 3 farad, over here you have 6 farad, and this is 2 farad. So in total, you will have the equation of C equivalent equals to 1 farad. Okay, so if you are given the circuit, the best way to solve it is using the circuit reduction technique. From if you can simplify the circuit first, which one in the equivalent capacitance circuit, so that's going to be the best way. Okay, so remember, don't try to simplify your circuit from left to the right. Okay, so just take from right to the left. Okay, what about the example 1.7? In order to calculate the equivalent capacitance for the circuit in these figures, okay, we take a step one by one. Okay, so if this is the first step, try to solve this first. So this is in series. How you detect that this actually in series? So in order to find out whether the component is in series or in parallel, for a series circuit you should have the same current current flow. Sorry, it should have the same current flow. Okay, the same current flow through the components. Right, for example this one, so I flowing to the 3 farad and the same current flows through the 6 farad capacitance. As for example over here, you will have two different current, right, I1 and I2. So from here you will get this as, you can simplify the 5 farad and the 15 farad. Okay, and this is in parallel. Alright, this is in series. So the first step you do is take this one, 5 and 5, this gonna give you 20 farad. Alright, and then we simplify the circuit into this one. Okay, you will need a few steps before you can solve the circuit. Right, and this one should have another one over there. Okay, for the next one is, this will give you 4 farad down there, and this is it. Okay, this is 2, this is 6, and this is 1. Okay, what happened to your 3 and 6? Okay, so the equivalent capacitance over there should be in something like this. This is in series, so you need to find out the equation, the value using 1/3 plus 1/6. Okay, again this gives you 2 farad. Okay, now what happened to these two? These two equivalent capacitors is in parallel. So in parallel you just add up these two. So you can rewrite this, or you can redraw this in terms of we cancel this out. Okay, and you can put this as 4. Okay, 2 parallel with 2 is actually 2 plus 2 farad. So it gives you this 4 farad over here. And then if I just draw the part over there, the last part over there. So this is gonna be your circuit over here. Okay, the triangle at this area, this circuit. So you can see that your 4 farad and this 4 farad is actually in series. So series circuit, you can calculate the equivalent capacitance using 1/4 plus 1/4. Okay, so from here you will get 4 times 4 divided by 8, so you will get another 2. Okay, so another 2 over here. So these two, you can maybe you want to put it over here like this, and this one can be cancelled out. Okay, 2. So here you get 2, here you get 6. 6 and 2 in parallel. Okay, 6 and 2 in parallel, so you no longer have this part now. I just redraw it over here. Okay, so this will be your case. This is your 20 farad, and this is your 1 farad. Down there you have 8. Over here just now you have 6 and 2 in parallel, so this area you will get 8 farad over here. 6 plus 2. Okay, this is it. Okay, now you can see that you have 8 and 8 in series. Okay, 8 and 8 in series, it gives you 64 divided by 16, you get 4. Okay, 4 farad is over here. Okay, so I just cancel this out, so it gives you like this. This is 1, this is 8, and over here you will get it in parallel, something like this. Okay, in parallel like this. Okay. Here, this one farad. Oh, sorry, 4 farad. 4 and 1. Okay, 1 and 4. 1 and 4 over here is in parallel, so this gives you 5 farad. Okay, so finally, when you simplify the circuit, you definitely will have this 5 farad over here, and this is the 20 farad. Okay, so a series circuit of the capacitance, you can calculate the C equivalent according to 1 over 20 plus 1 over 5. So over here we'll get 4 farad. Okay, that's the equivalent capacitance value for this circuit. Okay, so you can simplify your circuit as you wish. Okay, if you can handle this part together with this part, then it's okay. Otherwise, you do step by step, but it will take a longer time for you to complete your calculation. Alright.